Hello, everyone, and welcome back. Today, we're going to be talking about acid-base chemistry, but we're going to be going a little deeper than we had gone last time. So previously, we had discussed a little bit about Bronsted acid-base chemistry, and this time we're going to be doing more Bronsted acid-base chemistry. But the thing is, we do know from the previous lecture that taking something like HCl and sodium hydroxide, which we are already well aware HCl is a strong acid, and sodium hydroxide is a strong, I'm going to put this in quotes though, because we'll talk about later why this might not be entirely true. Base, we do know that this reaction proceeds to generate water and sodium chloride, right? And that is entirely because we are aware of everything that has to do with strong acids and bases. But what if we were given a situation where we don't necessarily have a strong acid or a strong base there to guide us, right? And the book gives a really good example of this, and it is a reaction that looks like this. The question becomes, what is the product here? And the first thing that we have to do to determine the product is the same as we've been doing for all other acid-base chemistry. We have to ask ourselves which of these is the acid and which of these is the base. But the thing is, neither of these, as we know, are a strong acid or a strong base. And so at this moment in time, there's not really a way for us to decipher what is what here. What we need to do is we need to get an idea of what makes something acidic and what makes something basic, and use that to build a framework for how we're going to determine which is the acid and which is the base. And so the first thing that we need to do whenever we're determining acidic protons is we need to ask ourselves what makes something truly acidic, right? So if we're doing this with something like HCl, right? We know that HCl as the acid becomes Cl minus once it reacts with a base, right? And we know from last lecture when we were talking about something being a strong acid, we said that it was inherently unstable, whereas a conjugate base of a strong acid is weak in terms of being a base, and thus it is stable, right? So we'll put over here that it's also weak. So, chlorine is clearly stable, but the question is, why is the chloride, sorry, stable? And that has to do with how well an atom or molecule can stabilize a negative charge, right? So, whenever we're looking at stabilizing a negative charge, there are multiple factors that go into this, right? So, there are five different factors that can stabilize a negative charge. The first one is atomic size, right? And we'll go through each of these and we'll kind of define exactly what is going on with each. But the first one is indeed atomic size. The second one is electronegativity, right? So the reason we brought in electronegativity so late is because it relates directly to this lecture. The third one is everyone's favorite. It is resonance. The fourth is something we call induction. And then the fifth is hybridization. All right. And these five different factors, I've listed them in order of relative importance, right? So going up towards atomic size, this is their relative importance. Thing is, though, keep in mind that this is not a set scale, right? It is not set in stone. And we'll talk about ways that we actually go through and think about these. That way you can determine when to use one versus the other. But overall, this is the relative importance that we'll say is generally true. So let's start out with the first one, right? Let's go into number one, which is atomic size. And the first thing that you need to know is Bigger is better. All right, that'll be our quote for atomic size. So in this case, size does make a difference for us. And what we can think of is we're going to just compare two things from the periodic table that are different in size, right? For each of these, we're going to give a very simple example. So for this one, we're going to take HF versus HCl. And we're going to think about which one is going to be more stable once it undergoes an acid-base reaction. So to do so, we're always looking at our conjugate bases. And we're asking ourselves, which is more stable of the two, right? Because F minus fluoride and Cl minus, which is chloride, these are going to kind of determine which one is a stronger acid. Because in essence, strong acids make stable conjugate bases, right? We see it with HCl, we see it with H2SO4. The question is why? So, the more stable a conjugate base, the more acidic the parent acid is. And so, when we're thinking about size for the fluorine versus the chlorine, right, I like to think of it in terms of something like a giant sphere, right, like a basketball. And fluorine is smaller than chlorine. And we know this due to periodic trends. So real quickly, I'll draw out a quick mock periodic table just so that we have um, these atoms where we want them to be, right? So here would be a periodic table that's very much so condensed, but essentially atomic size increases going from right to left, right? The more electronegative atoms pull things closer, so they're actually smaller. But the more important one is it greatly increases as you go down different rows. So in the different rows of the periodic table, we have huge increases in size, and it kind of makes this left to right increase really not matter for us. All we care about is the up and down. And so we can see that fluorine being directly above chlorine, right? Chlorine is greatly increased in size compared to fluorine. And so that's where we're coming up with these two bubble sizes here. So looking at this, if you imagine a negative charge, it's not just a negative charge. It's actually spread amongst the surface of the entire atom itself. So if we imagine it as being six partial charges, right, and that's just a random number we're making up here, but it's good for visuals, right? If we were to want to spread out six partial negative charges across this circle here on fluorine, we would space them out as equally as we could. And this is not a great equal distribution, but it's close enough. We can see that these negative charges are relatively close to one another, right? And this gives us repulsion from being near, right? And so this repulsion, as we know from talking about stability previously, is unstable, right? If we compare this to chlorine and we want to distribute the same charge, so the same six partial charges, we would distribute them more like this. And looking at this, we can already tell that since the charges are further apart, there is much less repulsion. And much less repulsion means for us much more stable. So size actually matters a lot for stability because it essentially distributes the charge across a wider area, which means that it's like there's less there, right? And the less concentrated a charge, the better it is. So when we're looking back at this question of which is more acidic, HF versus HCl, we know that Cl minus is more stable, which in turn means HCl is more acidic, right? Because of the statement that we made right over here. Stronger acids make strong or more stable conjugate bases. All right. So this is a good example. all right, of something being stable due to size. But let's do another example. So for this one, let's ask ourselves, which is more acidic, H2O or H2S? Right? Once again, if we're looking at that periodic table, close enough, we can see that oxygen is smaller than sulfur. So for the conjugate bases, right, we have OH minus, SH minus, and sulfur, as we just said, is bigger. We know that bigger is better in terms of stability. So SH minus is more stable. Therefore, H2S must be more acidic. Okay? So let's take a look at this effect in action. Because remember, we're starting to change the way that we think about these reactions. It's not just about strong acids and strong bases. Now we have to identify what's actually going to be doing the chemistry. So let's say we had a situation such as this one, where we have on a molecule both an OH and an SH, and it's reacting with some base with a negative charge. All right. What we have to determine is which one of those protons is going to be more acidic. And just like we saw up here, if sulfur with a negative charge is more stable than oxygen with a negative charge, that means it's going to be more acidic. So on this molecule, this right here is our most acidic proton. And if it's the most acidic, that means it's going to act as the acid. All right. So when our base comes in and grabs a proton, it's going to grab the one from the sulfur, which means that it's going to push some electrons back to the sulfur, and we're going to end up with a negatively charged sulfur. And our base will be happy because it got a proton. So, needless to say, for size, bigger is better, right? The bigger something it is, the better it can distribute that charge, the more stable it will make the conjugate base. Because as we talked about last time with our equilibrium conversation, the more stable something is, the happier it is to move to that equilibrium. All right, let's talk about the second effect now, and that is electronegativity. All right, and for this one, you just need to remember higher is better. All right, so what does that look like for us? Well, let's take an example of some electronegativities that we know, right? Let's say we were to do H2O versus CH4. If we were to lose a proton from each of these, right, it gets deprotonated. It would make OH minus, and it would make CH3 minus. All right. And so with electronegativities, if you remember what we talked about previously in our resonance chapter, we were looking at electronegativity increases as you move left to right on the periodic table. So if we're looking at this first row and we're moving over this way, this is increasing electronegativity, right? And so what that means is that oxygen is more electronegative than carbon. And when you're thinking about electronegativity, remember that this was thinking about which atom is pulling harder on electrons. So when we're thinking about this, we can think about how happy an atom is to have more electrons. And if an atom is more electronegative, it wants more electrons. So essentially what that means for us is oxygen likes the negative charge more than carbon, right? And so that means that it's actually stabilizing it more than carbon. So because of that, we can say that an oxygen with a negative charge is more stable, which means an OH versus a CH is more acidic. All right. Looking at another example, doing the same comparison. Let's say we were looking at HF versus NH3, right? A deprotonation of these would give us F minus and NH2 minus. And looking at our electronegativity table, we see that fluorine is more electronegative than nitrogen. So because of this, we can say that this F minus is more stable, right? It's happier to have the electrons, which means that HF is also more acidic than NH3. All right, so electronegativity matters a lot for us. And so if we want to take a look at this in action, right, once again, it actually making a difference in a reaction for us. Let's say we had a situation where we had this molecule here and it's interacting with some type of base, right? First thing that we have to think about is which proton is more acidic. And so we have to think about those conjugate bases. So we have a bunch of carbons with hydrogens attached to them, but we know that's a bad idea because carbon's not very electronegative. The other things we have is we have this OH and we have this NH, right? Oxygen being more electronegative than nitrogen tells us that the oxygen would rather be deprotonated and take that negative charge. So when we're thinking about the most acidic proton, this is our most acidic proton. So that means when our base comes in, it's going to grab that one, give the electrons to that oxygen, and we're going to end up with a negatively charged oxygen, the NH2 just chilling there, and then our protonated base. Okay? So, needless to say, for electronegativity, you're always looking at which has the higher electronegativity. But I do want to point out a caveat, all right? Because this is very important. Size always trumps. Oh, whoops, this is Trump. Electronegativity. All right. And the way that we can visualize this is we can take something that's not very, or something that's very electronegative, but smaller, and something that is more so larger and less electronegative. So if we were to take, for example, something like OH, H2O, sorry, that was written weirdly, versus pH 3, right? If we once again take a look at our periodic table, right? Phosphorus is in the row below oxygen. But if you were to look at the electronegativity table, oxygen is more electronegative than phosphorus. Thing is, though, it doesn't matter. That size still makes a huge difference for us. So when we're thinking about this as an example, right, if we're making OH minus and pH 2 minus, pH 2 minus is still more stable due to size. And even though oxygen is more electronegative, it doesn't matter. Size is more important here. So that means pH 3 is also more acidic. So keep this caveat in mind that if you're looking at something that is bigger but less electronegative, it's probably going to beat the thing that is smaller but more electronegative. All right, let's hop on to our third factor, which is resonance. And for resonance, I would say that the best quote that we can use here is sharing is stable. All right. So let's take a look at another example of two different possible acids. All right. So for these two, right, if we're asking ourselves which is more acidic, we have one that has that carbon double bond to an oxygen. We have one that's just a CH2. What does this mean though? Well, if we were to look at the conjugate bases here, right, we're clearly going to deprotonate the oxygen because it's very electronegative. The only other things here are carbons. And so we end up in these situations with these two molecules. But the one on the left-hand side, we can actually draw some resonance for, right? Because this oxygen can use a lone pair to form a pi bond there, break that pi bond, kick it up to that oxygen there, and that's going to give us a negative charge onto that oxygen. And so for these resonance forms, essentially what we're seeing is rather than a negative charge being completely focused on a single oxygen, it's actually being shared across two oxygens. So in reality, it's like rather than each oxygen having a negative charge, they each kind of have a minus one half charge. And if you're sharing charges like that, you're making something more neutral. And right closer to neutral equals more stable. So this is very close to neutral versus the other oxygen over there has a full negative charge. So what this means for us is that this conjugate base is more stable. And like we've said with everything that's more stable, that does mean that its acid is more acidic. All right. So that's a good example of resonance. Let's do another. So for this one, let's say we had, I guess I don't have to draw it out. I can just do NH2 versus this here, right? If we were to make the conjugate bases of these two compounds, we would end up in a situation where you have this NH minus and this N minus, and we have to ask ourselves is which is more stable. Well, the one on the left can actually perform resonance, right? It can make a pi bond here, break that pi bond, move it over there. In doing so, it's sharing its negative charge with a carbon. And even though we know carbon does not like to be negative, that doesn't take away from the fact that it is still sharing. And as we know, sharing is stable. And it can share with multiple carbons, which is even better for us, right? Because the more we can share, the better off we're going to be. And so there's these three resonance forms that we can draw that are all different, which is showing the negative charge being shared amongst all of these different atoms. And so if we're asking ourselves which is more stable, it's clearly this one here because it is sharing those electrons with all those carbons versus having the negative charge directly on the nitrogen not being shared at all. So that lets us also know that the compound on the left is more acidic. All right. So resonance is very important. But here's the thing. The type of resonance matters. All right. So an example of this would be let's take those last two examples we've done and kind of combine them. Right. So let's say we had this structure from the first example and a structure very similar to the second example, right? If these were to undergo acid-base chemistry and become deprotonated, we would end up with something that looks like this. And so since I've just drawn all the resonance forms, I'm not going to redraw them all out, but I will put the partial charges where they belong, right? So the question is, which matters more for us? We have on the left-hand side an oxygen that shares the electrons with another oxygen, or on the right-hand side, we have an oxygen that shares the negative charge with three different carbons. Well, the answer is actually that sharing with highly electronegative atoms is better than sharing with multiple non-electronegative atoms. All right. So what that tells us is sharing with those carbons doesn't do as much in terms of stabilizing as sharing with something like another oxygen, right? Because the oxygens want the negative charge more than the carbons, so it means that they are happier with that negative charge. So that tells us that this compound here on the left is more stable, which means that this right here is also more acidic. And funny enough, you all should have already known that this is indeed an acid because the functional group name is a carboxylic acid, right? It's very acidic because it can share the negative charge amongst those two oxygens. All right, let's take a look at this effect in action. Just like before, we can put a bunch of different things onto the same framework. So we'll add on a bunch of nitrogens here. All right, and if we bring in some type of base with a negative charge, we have to ask ourselves which of these is going to get deprotonated. Well, there's three possibilities, right? Because when we're looking at this, we know that the nitrogen is the most electronegative element that has a hydrogen on it, right? Because the oxygen there doesn't have any protons attached. It's just an O. So, knowing this and looking at these other nitrogens, we have to ask ourselves which one's going to be most acidic. And we actually have an order that we can rank them with. Because we should know by now that the one over here is the most acidic, right? Because that nitrogen is able to then share the electrons with the oxygen. The second most acidic would be this one down here, because this can then share with the electrons in the ring. And then this one over here is our third because it has no capability of performing resonance to share. And so with that being said, when we're looking at our acid base that happens, it's going to deprotonate the most acidic proton that we had labeled there as first. And so we're going to end up with the NH minus, and then these other nitrogens are just going to have the protons that they originally had. All right, now that we've done resonance, we have two others, and these are a little bit quicker to explain. So let's look at our fourth effect, which is induction. And what I would say for induction is other atoms matter. All right. So what this means is if we take a look at a structure that is very similar, we'll do two different structures that look almost the same except for one small difference. All right. So the structure on the left, you'll notice, has a bunch of fluorines, whereas the structure on the right does not. If we were to look at the conjugate base of these, we would see that both of them still make an O minus, and none of the effects from before actually apply, right? Because there's no difference in size, there's no difference in electronegativity, there's no difference in resonance. We just have a situation where one of these is more acidic than the other. Looking at which one would be, the fluorines are going to make a big difference here because fluorines, as we know, are very electronegative. And what that means is that they're all pulling dipoles towards them. All right. What this is going to do overall is the more dipoles you have in one direction, the more of an overall dipole you're actually going to have. And if we're thinking about the overall dipole on this molecule, it's going to be pulled very, very far towards that fluorine. And if you all remember us talking about dipoles previously, we said that the side that the arrow points towards is partially negative, and the side that the arrow points away from is the partially positive side. And you'll notice that partial positive is pretty close to where our negative charge is. And in essentially, the partial positive charge and the full negative charge, if you add those together, that's going to give us what is essentially a partial negative charge. And so this is less negative than the original negative charge, which means that it is closer to neutral, which means that it is more stable. So that tells us that when we're looking at these two molecules, this one right here with all those fluorines is more stable, meaning that the one up top is more acidic. All right. So the other atoms that surround the atom that you're messing around with are important. But keep in mind that induction as an effect, right? Those first three that we talked about are incredibly important. This one is much, much, much less important. All right. And the reason that we put them in the order of relative importance is because, relatively they are pretty important, but there's a big difference between resonance and induction, and that is going to show when we're looking at acidic protons. Okay? So let's look at this effect in action. Right, let's say that we had a molecule that looks like this. All right. So looking at this, we have two OHs, which we know are going to be relatively acidic, but each one is surrounded by different atoms. Right? One has two fluorines pretty close to it, the other one has two chlorines pretty close to it. Distance matters because the closer the atoms are, the more they're going to be pulling on electrons near them. The further something away is, the less that it's feeling that pull. So if we're taking a look at these two sets of atoms, the question that we need to ask ourselves is which is actually more electronegative of the chlorine or fluorine? Because those are going to be doing more of that uh, pulling effect where they're going to give more of a partial positive charge to whichever oxygen they're closer to. And looking at the periodic table, we do know that essentially, oxygen, fluorine, chlorine's down here, right? Fluorine is the most electronegative, and therefore it's going to be pulling the strongest dipole towards it, right? So if we were to show two different dipoles, we can see that the one by fluorine is much more of a big arrow. So what this means is that it's going to be better for us to deprotonate the oxygen closer to the fluorine. It's going to stabilize it more by taking away more of that negative charge. And so that makes that our most acidic proton, and that would be our product. Okay? So more electronegative means more induction. Let's take a look at our final uh, type of effect, which is hybridization. Funny enough, you all already actually know how hybridization affects it. You just don't know you know it yet. So let's take a look at what hybridization is. And essentially, for this one, the quote that you want to remember is closer to nucleus is better. All right. So we can take a look at two different compounds. All right. So we have ethane versus acetylene, CH3, CH3 versus HCCH. And so looking at these, if we were to deprotonate each of them, right, now we have to deprotonate some carbons. So looking at what that's going to look like, we will end up with a negative charge on a carbon over here. And for this one, we'll end up with a negative charge on that carbon there. And now you already know that this has something to do with hybridization, right? And the reason we know that is because if we look at the difference between these two molecules, they have the exact same electronegativity, exact same size. There is no difference in resonance between the two. There is no difference in atoms that are connected to each atom, which means there's only one option, and that is hybridization. So looking at the hybridization between these two, the one on the left is sp3 hybridized, right? It has all sigma bonds and it has that lone pair, but the lone pair can't do resonance, so it's just in its own sp3 orbital. Versus over here, this is an sp hybridized carbon. So what this means for us is we have to ask ourselves which is stabilizing the negative charge more. And this is where our favorite diagram comes back into play of distance and energy from the old positively charged nucleus. And as we know from many times before, the less p character something has, the closer it is to the nucleus. And so the sp orbital is closest. And why this matters is because we're essentially putting a negative charge in that orbital. And so we're either putting it in an sp in the case of the right molecule, we're putting it in an sp3 in the case of the left molecule. But as we've said a couple times before, negatives and positives are attracted, right? And this is a stable effect. And so the closer we are to the positive charge, the better. So that tells us that this, being closer to the nucleus with the negative charge, is more stable, right? Because the nucleus is always positively charged. So what that means when we're looking up here is the sp hybridized carbon with the negative charge is more stable than the sp3 hybridized. So that does mean that up here, this carbon with the triple bond with the C as the CH is also more acidic. So let's take a look at this effect in action. So looking at this, let's say that we had a structure that looked like this. Now you're probably not going to ever see something like this. Keep in mind, because at the moment, it's something with two positive charges. It's probably not going to happen, but nonetheless, it helps demonstrate the point here. So looking at this, we have two different oxygens, same electronegativity, no special resonance that we could do if we deprotonated them. There's no induction, which means that this must be a hybridization problem. And looking at these two, the one with the double bond is sp2 hybridized, right? Because it has a pi bond, so it needs a p orbital there. And then the one with just sigma bonds is sp3 hybridized, because remember that this one does have a lone pair still, but it just sits in an sp3 hybridized orbital. So what that tells us is if we're going to deprotonate one, we want to deprotonate the one that is sp2 hybridized, right? Because that's going to put the electrons closer to the nucleus, which is better. So that means that it'll deprotonate it. You'll end up with the neutral oxygen and the happy base. So we've gone through the five different ways to determine if something is acidic. All right, and just as a recap, size, we want it to be bigger, right? Electronegativity, we want it to be higher. Resonance, we want it to be shared, right? We want the charge to be shared. Induction, we're looking for other electronegative atoms. And then finally, for hybridization, oh, sorry, that looks terrible. We want it to be closer to the nucleus. All right. And so the thing that we gotta, sorry, I need to just scoot this down a little bit. So the thing that we gotta remember is this is for acidity, right? And the other thing that we want to keep in mind is that these top two, generally speaking, we are asking ourselves about different atoms. Versus the bottom three, we're generally looking at the same atom, but we're looking at its surroundings. All right. And this kind of gives us the idea of how we're looking to see if something is acidic, right? So, if we want to return to that original question that we asked at the very beginning, right? Which was, what happens if we mix these two things together? right? We have to identify the acid and we have to identify the base. And how we do this is it's generally a two-step process, right? Step one is always asking what is the most acidic proton? And then step two is to ask yourself, then what is the base? So let's look and let's see if we can determine what the most acidic proton is here. First thing that we want to think to ourselves is size. Are there any really big atoms here? Not necessarily, right? There's nothing from that second row of the periodic table, no sulfur, phosphorus, chlorine. So the next thing we have to look at is electronegativity. And what I'm seeing is we have a nitrogen with a hydrogen, oxygen, and another oxygen. So that's telling us that there is some likelihood of these being the most acidic proton. And as a matter of fact, we can actually eliminate the NH2 because it is the least likely because it's the least electronegative of the group. So that tells us that's probably not the most acidic proton, but the other two are oxygens. They're the same. So we got to take a look further. Question then becomes resonance, right? Is there any resonance that we can perform? Looking at the compound on the right, deprotonating that would give us some resonance stabilization. So it is relatively fair for us to say that this proton right here is the most acidic proton, which is great. But now we have to answer the second question, which we haven't talked about this entire time. What is the base? And the funny thing is, for bases, we can use our exact same scale, right? And we're going to look deeper into this next time. But for right now, you just need to know that all of the same effects are important. It is just the opposite of the effects. So if we're looking at size, we want it to be smaller. If we're looking at electronegativity, we want it to be less. If we're looking at resonance, we want it to not be shared. If we're looking at induction, we want there to be no electronegative atoms around. And if we're looking at hybridization, we want it to be further away. So looking at this up here, essentially the only other criteria for a base is a base must have, I'll spell it all the way out, lone pair electrons, right? That will come into play later, but for right now, if we're looking at the thing that we said was not the acid over here, right, we do have stuff with lone pair electrons. We have the nitrogen and the oxygen that both have lone pairs. The question is which one of those is most basic? And if we're looking through our list of what bases want, right, their difference in size is relatively minor. They're in the same row. Electronegativity wise, we want the one that is less electronegative. And looking at the two, nitrogen's less electronegative than oxygen. So that tells us that this is our most basic atom. And again, we will go deeper into this at a later time. But for right now, we have our most acidic proton, we have our most basic atom. So let's draw out what the reaction's going to be. Right? The nitrogen electrons are going to come over, grab that proton, kick the electrons back to that oxygen, and we're going to end up with our product, which has that NH3 plus, because remember that nitrogen just gained a proton. And then we have our O minus right there. So this is kind of how we're going to have to start approaching these problems. We're going to have to ask ourselves, what's the most acidic proton and what is the base? And in a supplementary video, I am going to give some examples of these, right? And we're going to go through and we're just going to do some problem solving, talking about reactions, looking at how do we identify the base, how do we identify the acid? And then in your practice problem worksheets, you're going to get a full masterclass in going through what is an acid, what is a base, and figuring it out from there. Next time, we'll start talking about equilibrium in these reactions, and it'll start giving us a good idea of what is actually favorable versus what is not favorable. So with that being said, I'll see you all next time for that video.